We've seen that viewing a matrix as a machine that transforms vectors allows us to often interpret problems involving matrices and vectors geometrically. So I want to take a closer look at the geometry of certain types of matrix problems. And a good way to do this is by introducing what's called fundamental subspaces of a matrix. The first of which we'll study is the null space of a matrix. So what is the null space of a matrix? By definition, the null space of an n by n matrix is this. So we use the notation NULL of A. And what this notation tells us is that we're going to look at all vectors V in Rn. So here n denotes the number of columns of the matrix. And this vertical line here is the math symbol that says that satisfy. So we're looking at all vectors V in Rn that satisfy. And we're interested, when we're discussing the null space, in the equation A times V equals the zero vector. So if you want to check whether or not a vector is in the null space of a matrix, what you do is you take A, your matrix, you multiply it by the vector, and you verify whether or not you get the zero vector. So we write V belongs to null of A to indicate that A times V is the zero vector. So here we're looking at two examples where we take the same 4x3 matrix A and we multiply by two different vectors in R3. So on the left here, we're multiplying by this vector V, and on the right, we're multiplying by this vector W. What's interesting about this example is that when we multiply our matrix A by the vector V, we produce the zero vector. And what this tells us is that this vector V belongs to the null space. On the right here, we see that when we take our matrix A and we multiply by this vector W, we definitely do not produce the zero vector. So this vector W does not belong to the null space. So some vectors belong to the null space, some vectors don't. And the way we distinguish between the two is by just multiplying by A and checking whether or not we get the zero vector. It's also quite common to see the null space referred to as the kernel of a matrix. We'll use the terminology null space, but the terminology of kernel is out there. Okay, so remember, whether or not a vector belongs to the null space hinges on whether or not, when we multiply that matrix by the vector, we get the zero vector. So again, we have examples here. On the left, we're taking a 3x4 matrix, and we're multiplying by this vector W1 in R4. And when we do this matrix vector product, we produce something that is definitely not the zero vector. So what that's telling us is that this vector W1 does not belong to the null space. On the other hand, over here, we have that same 3x4 matrix, and we have another vector W2. This vector belongs to R4, and again, 4 here is the number of columns of the matrix. And when we multiply A by W2, we produce the zero vector. So here, this vector W2 does belong to the null space. Now, so what we're saying here is that if someone gives you a vector and they ask you, is it in the null space of this matrix, the task isn't terribly difficult. We just need to take the matrix and multiply by the vector and check if we get the zero vector. On the other hand, if someone asks you to describe all the vectors in the null space, we have a bit more of a difficult problem on our hands. Because really what they're asking, if someone asks you to describe all vectors in the null space, is they're asking you to solve a system of equations of the form AX equals the zero vector. And the way we solve systems of equations is by doing row reductions. So I can take the same matrix we started with up here, and if I'm interested in actually describing everything in the null space, I need to set up the system AX equals 0, which is obtained by taking A and augmenting with the zero vector. Then I do my row reductions over here. And what I find is that when I do my row reductions, of course I get a consistent system because I don't have a pivot in the augmented column. I have 2 dependent variables and 2 free variables. And when I go through the process of writing the dependent variables in terms of the free variables, what I'm finding here is that the vectors that live in the null space of our matrix are exactly all of the linear combinations of the vectors 2, 1, 0, 0 and 3, 0, negative 7, 1. So here what we have is an explicit description of all vectors in the null space of a matrix. This problem is significantly harder than simply verifying whether or not something is in the null space. So again, to verify whether or not a vector is in the null space of a matrix, we simply multiply by A and check if we get 0. If we want to describe everything in the null space, we have to augment our matrix with the 0 vector, do the row reductions, and write down all solutions to the system. The difficult part there, of course, are the row reductions. Row reductions are computationally expensive, which is why it's more difficult to produce all vectors in the null space than it is to verify whether or not a given vector is in the null space.